Hello everyone, welcome to my channel Chemistry is Fun. Today we will be dealing with the topic kinetic theory of gases, and also I will deal with the kinds of molecular speeds. So as we know, if we want to study the properties of gas, then we can study the action of the molecules of the gas. So if we want to study the action of the molecules present in a gas, we can use a theoretical model. So this model is called the kinetic theory of gases. In this, some assumptions are made, as we will see in the postulates, because we know that the molecules are very small relative to the distance between the molecules. And also in the gas, as we know, the intermolecular space is very high. The molecules are in constant random motion, and also they will collide with each other. They also collide with the walls of the container. So keeping all this in mind, the model which we get is known as kinetic theory of gases. So let's get started. Now see, this kinetic theory of gases, it was given by Bernoulli, and later on it was developed by Clausius, Maxwell, Croning and Boltzmann. As I just told you that it is a theoretical model, and in order to understand that, some postulates have been given. Now in the syllabus of JEE, we have to study in detail the postulates of kinetic theory of gases. Now as per this, the first postulate states that the gases are made up of molecules. Okay, and if it will be atom in the case of noble gases, because noble gases like helium, neon, krypton, they do not chemically combine because their octet is complete. So that also we have to keep it in mind. So in general, gases are made up of small structural units which are called atoms in case of noble gases, and in general all other gases you take oxygen, nitrogen, hydrogen, they are in the form of molecules. And as I just told you, the space between the molecules is very high in case of gas. So if we consider the volume of individual atom or molecule, that will be negligible. And the gas molecules are always in constant rapid motion. The motion is also random. So they continuously collide with each other and also with the walls of the container in which the gas is kept. Whenever this collision takes place, there will be no loss of kinetic energy or momentum. So this is a perfectly elastic collision. No loss in kinetic energy, so kinetic energy will be maintained, as well as the momentum that will be conserved. There is no loss in either of the two physical parameters. It is also taken that the gas molecules do not attract each other, neither they repel each other. The pressure exerted by the gas is because of these collisions with the walls of the container, because the gas is kept in a container. So when the gas molecules collide with the walls of the container, they exert a pressure. That pressure is taken as the pressure exerted by that particular gas. The kinetic energy of the molecules depend on absolute temperature, and the speed of the molecules is not affected by force of gravity. That is, force of gravity will have no effect on the speed of the gas molecules. So these are the postulates based on which we have the kinetic theory of gases. Now next is the molecules exhibit certain speeds which we will consider. They are of three types: molecular speeds: root mean square speed, average speed, and most probable speed. So we will deal with these three one by one. First of all, the root mean square speed. Now in kinetic gas equation, the speed is the hypothetical speed which is possessed by all the gas molecules, and in this case it is true when the total kinetic energy is equally distributed among the molecules. So we have the equation as PV equal to 1 by 3 mnc square. So this is kinetic gas equation, PV equal to 1 by 3 mnc square. Now see, as I told you, in this case is possible when the total kinetic energy is equally distributed among the molecules. So we need to know what is the total kinetic energy. The total kinetic energy can be given as the sum of all the kinetic energies of the n number of molecules. So it will be half m c1 square plus half m c2 square up to half m cn square. So these are the velocity. C is the velocity, in this case half m c1 square I told you. This C is the velocity possessed by each of the n molecules. So for first molecule C1, for the second one C2, like that. So if we take that C is the velocity for each of the n molecules. So there are n number of molecules and velocity of each of them is C, let's say. Then the total kinetic energy will be given by n multiplied by kinetic energy of single molecule. So that will be n into half mc square. Half mc square into n, because n is the total number of molecules and c is the velocity possessed by each of the molecules. Now equating both the equations, this one and this one. So initially we told that this is the case, first one, when the total kinetic energy is equally distributed among the molecules, and then we take a sum total by generalizing that velocity possessed by each molecule is c, and then there are n number of molecules. So if we equate both the equations, we get n into half mc square will be equal to the addition of half mc1 square plus half mc2 square up to half mcn square. So m, if you take common, it will get cancelled on both the sides. So c square will be equal to c1 square plus c2 square up to cn square divided by n. And c will be equal to square root of this, that is the square root of the mean of the squares of the speed, that is c1 plus c2 square, c1 square plus c2 square up to cn square divided by n, that is the mean of the squares of the speed of all the molecules, and a square root of that equal to c. So that is RMS, root mean square speed, is defined as the square root of the mean of the squares of the speed of all the molecules present in given sample of gas. So and also here it can also be expressed as C is equal to square root of 3 PV by M. So these equations can be used for solving the numericals. In this case, where C is equal to square root of 3 PV by M, P will be in kilopascal, M will be in kg per mole, V will always be in liters. C can also be expressed as in case of RMS, square root of 3RT by M, where value of R will be 8.314 joule per Kelvin per mole. So these are the values, these are constant. So this we need to remember when we do the numericals. So these both the equations can be used for C in case of RMS speed. Next is average speed. Average speed is the arithmetic mean of the various speeds of the molecules. Means we take various speeds, add them, divide by total number of molecules. General, how we take average, that one only. So average speed will be equal to C1 plus C2 up to Cn divided by n. This can also be expressed as square root of 8RT by pi m. RTM, all these I told you what it stands for, values. I told in RMS, same will continue here. T will be the temperature, temperature in Kelvin. Next is, if we see the relationship between average speed and RMS speed, average speed will be equal to 0.9213 into RMS. So this is the conversion. Directly if we get some numericals and you can calculate the RMS speed, from that if you want to average speed, just multiply by 0.9213. So these we can remember for solving the problems. Third is most probable speed. That is, in a molecules, different molecules have different speed, but there will be a speed which is possessed by maximum number of molecules of a gas at a particular temperature. So that speed is the most probable speed, means more number of molecules possess that speed. And if it is compared with RMS, we get most probable speed equal to 0.816 RMS. So we also have a generalization for most probable speed in terms of R and T and M. Most probable speed is given by square root of 2RT by M. So we can compare the ratios of the three types of speed we have just seen: most probable speed, average speed and RMS speed. So most probable speed is to average speed is to RMS speed will be given as the ratio which I just mentioned, because most probable speed is square root of 2RT by M, we keep it here. Average speed is square root of 8RT by pi M is to square root of 3RT by M. So here you see the common factors R, T and M are there in all the three, get deleted. So we get square root of 2 is 2. Square root of 8 by pi is to square root of 3. So on calculating we get 1 is to 1.128 is to 1.224. So this is the final ratio. So this can be used for interconversions. If you know one speed, you can get the value for the other one. Now let us have a quick look at some of the examples which I will be solving now. These are not already solved, I am solving. Calculate the root mean square speed of an oxygen molecule at 288 Kelvin in SI units. So root mean square speed we have to find out. We start with the formula I've just given you. We know C equal to square root of 3RT by M. Then we put the values. R will be equal to 8.314 kilopascals dm cube per Kelvin per mole. Per Kelvin per mole. And here given temperature is 288 K. They have given in the sum, they have given it. T is equal to 288 Kelvin. We have to use this value. Now since it is oxygen, so it will be per mole, the mass will be 32 grams. But MK system we are using, so we need to convert it into kilograms. So mass will be equal to M equal to 0.032 kg per mole. So this value also need not be given because we can calculate. We should know the molecular weights of the common elements. Putting all these values, we get C equal to square root of 3 into 8.314 into 288 divided by 0.032. Now this is simple mathematical calculation. We need to do the multiplication. If you multiply, we get 7183.29 divided by 0.032. On this division we get at equal to, these are simple multiplication and divisions, I am not doing in detail here. We get square root of 224,478. On taking square root we get it as equal to 473.79. Now since we are calculating the speed, unit will be meter per second. That is the unit in MCAS system, because the units we have taken are all in MCAS. So this is the answer, 473.79. Next is calculate the average kinetic energy per mole of CO2 gas at 27 degrees C in different units. Now see, kinetic energy will be equal to 3 by 2 nRT. So we use that formula. 3 by 2 nRT. Here R we have to take is 1.98 in calories. R equal to 1.98 calorie per mole per Kelvin. This we have to take. And for N will be equal to 1. Temperature T they have given 27 degrees C. 27 degrees C will be equal to 300 Kelvin. So putting the values we get equal to 3 by 2 into 1 into 1.987 into 300. On multiplying we get it as 894.15. Now the R value when we have taken, no, the unit used was calorie. So here energy will be in calories. We have not calorie, we have taken R equal to 1.98 calorie per mole per Kelvin. So the kinetic energy value will be in calories. Now we can also get the kinetic energy value in joules. So here then we have to use a suitable R value. KE is equal to 3 by 2 nRT. Formula is same. R value we are putting different. Here we will take R as 8.314 joule per mole Kelvin. We will take R is equal to 8.314 joules per mole Kelvin. So that amounts to 3 by 2 into 1 into 8.314 into 300, because in Kelvin this is the temperature. On multiplying we get it as 3741.3 joules. So this is the value in joules, 3741.3 joules. If we convert it into erg, we can get it as 3.741 into 10 to the power 10 erg. So we got in 3 different units, calories, joules and erg. Why it will be 3.741, I'll tell you. See, we got here earlier 3741.3 joules. It can be written as 3.7413 into 10 to the power 3 joules. That this will be equal to this, you see. This can be written as equal to 3.7413 into 10 to the power 3 joules. So for joules to work, we have to multiply by 10 to the power 7. So on multiplication, we will get 3.741 into 10 to the power 10 ergs. This number is 3. I hope you all could understand the topics which I discussed today. Thanks for watching my video. Please subscribe to my channel. Please subscribe to my channel. The channel is free. All the material, study material is everything is free for you all. If you subscribe my channel, it will help me a lot. You will also be benefited. So please subscribe my channel. Thanks for watching the video. Thank you.